Hello everyone, welcome to our last lecture for HEMI 5030 this semester. For today's lecture, I know have been taking up a lot of your time in terms of the lecture that I've been posting on YouTube. It's kind of long compared to the 1 hour 20-minute class because this is mostly because I want to complete the problems. But I think for today's lecture, maybe the good news is I might actually finish on time or maybe even earlier than that. Okay. All right, I hope you're all doing well and staying safe and healthy. My plan for today's lecture is to look at the motion of a heavy symmetric top, most predominantly to derive the equations of motion for a heavy symmetric top. And then we will discuss the idea of steady precision, fast precision versus slow precision. Okay, that's the last thing that we will be doing. Okay, all right. So aim for today is the following. So aim is to look at the equations of motion of a heavy symmetric top. Okay, so we will be looking at the equations of motion of a heavy symmetric top. Okay, and heavy symmetric top, what is the meaning of this word heavy? What is the meaning of this word symmetric? Okay, so heavy symmetric top implies the following. Okay, so heavy symmetric top implies the word heavy represents the fact that there is going to be gravity acting on the motion of this top, and there is going to be a weak torque due to this gravity. Okay, so the word heavy denotes that gravity acts on the torque during its motion and produces a weak torque. Okay, and produces a weak torque that affects the motion of the top. Okay, that affects motion of the top. Okay, and this is different from what we had seen when we started the semester and when we started looking into rigid body equilibrium, rigid body equations using Newton-Euler formulation. We had looked at the idea of a free top. Okay, so this is the opposite of that. This is a heavy symmetric top. So I just want to point out that earlier we had looked at earlier in the semester we had looked at the free symmetric top. Okay, and we had looked at certain terms like the wobble rate and the spin rate and so on. Okay, and we had looked at the wobble rate, spin rate, etc. Okay, of course, if there was time, we would have done the same thing for the heavy symmetric top as well. But I want to focus mostly on obtaining the equations of motion by doing the Euler sequence, the 3-1-3 Euler sequence, and then we will look at some nice things that come out of this. Okay, the word symmetric. So here we have defined the word heavy. So heavy denotes that gravity acts on the top during its motion. I guess I should have written this as a top, not a torque. Okay, so gravity acts on the top. Okay, during its motion and produces a weak torque. Okay, which kind of affects the motion of the top itself. Okay, that affects the motion of the top. But this is as opposed to the idea of a free symmetric top. All right, and the word symmetric implies that when you look at the principal axes for the top, the moment of inertia about two of the principal axes is going to be the same. Okay, so the word symmetric implies the following. Okay, so symmetric implies that the moment of inertia about two of the principal axes of the top are equal. Okay, and of course we need to describe how exactly the symmetric top looks like, and we have seen this in the past. So this is an example of a symmetric top. If I'm drawing one here, and then if I look at the principal axis, let's say that this is the center of mass of the top. Okay, so this is the center of mass, which I'm going to call as point G. Okay, and if I set up a coordinate frame that passes through the point G, I know I'm going to have one coordinate system here. Let me just scoot that up and make sure that's aligned with the point G. Okay, here is the point G, and then I have one more coordinate frame. Let's say that this is the other principal axis for me, and then I have the third one, which is going to be passing through here. Okay, that's going to be the following. Okay, so if I call this as E1, E2, E3, okay, then we can say that okay, G is the center of mass of the top, okay, and then E1, E2, E3 is the principal axis, for the top. Okay, and if I look at the moment of inertia matrix, I'm going to get the following. So I CM about the 1, 2, 3 coordinate frame. Of course, this is going to be a diagonal matrix, as we know. Okay, this is going to be I1 0 0 0, I2 0 0 0, I3. All right, and if we look at I2 and I1, they will be equal to each other. So the word symmetry implies the following. Okay, implies that I1 is equal to I2. I'm going to call this as some I prime. Okay, and then I3 is not the same as I1 or I2. Okay, all right, so this is the definition of the symmetric top. All right, now what we want to do is we want to obtain the equations of motion. We want to use a Lagrangian formulation, but we have to specify certain things before we go ahead and do that. Okay, so one thing that I want to point out is I'm going to call this point here as the point O. Okay, this is the point O, and in deriving the equations of motion of the heavy symmetric top, we are going to assume that this top is spinning on a very, very rough surface, such that the point O does not have any motion whatsoever. Okay, so when we are looking at the equations of motion, so the problem for us is the following. Okay, so problem. Okay, we need to derive the equation of motion of a heavy symmetric top okay, spinning on a fixed rough horizontal surface, spinning on a rough horizontal surface, okay, such that the contact point of the top and the surface does not have any velocity. Okay, this is the constraint that we are actually imposing upon the top. Okay, so in a sense, this is the constraint that we are imposing upon the top. Okay, the contact point of the top and the surface does not have any velocity whatsoever, so this is a constraint that we are imposing. This is different from the equation of motion for a rolling coin. This is because in a rolling coin, the contact point, of course, is rolling without slip, but that still means that there is going to be some translational motion of the center of mass of the coin. Here the center of mass of the top does not translate, and so we will see that this kind of reduces the number of degrees of freedom and so on. So I'm going to bring this top here. So this is our symmetric top. Okay, we're going to start off with that. I'm going to copy that and bring that here. Okay, so this is going to be I guess the situation that we have. Okay, not sure where this creature came from. Okay, so this is the situation that we have, and E1, E2, E3 is the principal axis of the top. This is shown at some this is shown in the initial position. If you want to think of it this as the initial position, this is completely fine. Okay, and I want to say that the distance from the point O to the point G is a distance L. Okay, so I'm going to call this distance here as a distance L, and I think I want to give this a different color maybe. Okay, all right, and likewise I guess for the same term here, I'm going to call it by a different name as well. So let me bring that guy down here. Okay, and this is going to be length L. Okay, all right, so how do we do this? We first of all see, okay, what are our configuration coordinates for the problem? Okay, so we set up the configuration coordinates. Okay, the first thing is location of the center of mass. Capital G. Okay, the second thing is because the top is spinning, we want to characterize its spin using the Euler angles. Okay, characterize the spin of the top, characterize rotation of the top via Euler angles. All right, so which means that if I look at the configuration coordinates, I have the following. Okay, so configuration coordinates. These are X, Y, and Z. This is the location of the center of mass. Okay, then I also have the Euler angles, which I'm going to call as phi, theta, and then psi. These are the Euler angles, and we have seen the labeling of these as the following. When we looked at the equation of motion of a rolling coin, the angle phi represents precession motion, then the angle theta represents nutation or the lean angle, and the angle psi represents the spin of the top. Okay, this represents the spin of the top. All right, so these are the things that we have. Then what we have to do is we first have to look at constructing the 313 sequence for the Euler sequence in order to characterize the angular velocity of the top. And then once we have that, we will impose upon this top the constraint that the point O has to have zero velocity. Then we will see that, okay, this and this is almost as if it's a fixed point. So if you want to, you can think of this point here. This is almost like a fixed point. Okay, and then once we have that, we will know what the velocity of the center of mass is. Once we have the velocity of the center of mass, set up the Lagrangian, and then we go ahead and solve the problem. Okay, so what are the steps for the solution? Okay, steps towards the equation of motion. We have already done a few of these. Okay, the first step obviously is to set up the configuration coordinates. Okay, so choose configuration coordinates for the top in order to characterize its motion. Okay, then we look at constructing the angular velocity of the top using the 313 Euler sequence. Okay, so construct the angular velocity of the top using the 313 Euler sequence of rotations. Okay, once we have that, then we will try to impose the constraint that the point O, the contact point between the top and the rough horizontal surface, is fixed. Okay, so then impose the constraint that point of contact between the top and the ground is a fixed point. Okay, so there is no displacement, there is no velocity, there is no acceleration for that point O. So this refers to point O in the first figure. Okay, refers to point labeled as O in the figure above. Okay, so once we have the constraint, then we set up the Lagrangian. Okay, set up L is equal to T minus V. We recognize what the system is, whether is it holonomic or non-holonomic. Then can we come up with the generalized coordinates and then apply the Lagrangian formulation, whether you use generalized coordinates or multipliers. Okay, set up the Lagrangian and then apply the formulation. Okay, to find the equations of motion. Okay, so these are the steps towards the equation of motion. And so my first setup is going to be looking at the top, okay, and then construct the 313 Euler sequence. And in order to do that, I'm going to do some simplifications here. Okay, so we have chosen the configuration coordinates for the top. That's done. So we will do the 313 Euler sequence for the top. Okay, that's our next step. Okay, so the 313 Euler sequence of rotations. This is our next step. Okay, and here is what I'm going to do. I'm going to take this top figure from here. Okay, I'm just going to steal this guy, and I may have to get rid of some of these terms there. Okay, I'm going to take this and do the following. Okay, I'm going to get rid of these guys, get rid of that as well. Okay, then get rid of that. I'm going to get rid of all of those creatures as well. Okay, cut that off, and then I'm going to cut that off, and I'm not really interested in that at this point in time. Okay, so that's the point. Oh, okay, so the first thing I got to do is I have to start with the reference configuration of the top. Okay, so I'm going to say this is the reference configuration of the top. In order to do that, so step A, okay, we start with a reference configuration of the top. Okay, and in this this is the reference configuration that I'm labeling here. So this is the reference configuration, and in this configuration the top is called as a sleeping top, and you'll see the reason why very soon. Okay, so this is an example of a sleeping top. Okay, so this is a reference configuration, and what I'm going to do is I'm going to say that, okay, I'm interested in so here is probably where the center of mass of the top is, right? I mean, if I align this properly, okay, so here is probably where the center of mass of the top is going to be. Okay, so here is the center of mass. Now what I'm going to do is I'm going to look at a small plane that passes through that I'm going to slice through. Okay, and I'm going to start off with the reference configuration labeled as the following. So I have my x, y, and z axes first of all. Okay, so I have this is my inertial frame. Okay, I'm going to set up an inertial frame first of all. Okay, and that's my inertial frame. I guess in a sense I don't need that for the time being. I'm just setting up an inertial frame at that particular point. Okay, so I'm going to call this as E capital X, and then I'm sorry, that was unnecessary. Okay, and then I'm going to call this as E capital Y, and then this is E capital Z. So in this situation, this is the inertial frame set up at the point O. Okay, so inertial frame at O is E capital X, E Y, and E Z. Okay, then what I'm going to do is, okay, instead of worrying about all of these, I'm just going to look at a very small section of this top, and then I'm going to continue forward with that particular idea. So I'm just going to duplicate that, and I'm going to bring that here. Okay, and I'm going to just show you that, okay, if I look at this, and if I say that it's not filled, and here is the situation that I have. Okay, I'm going to have a pair of axes which will be parallel to the EZ, EX, and EY coordinate frames. So I'm just going to label them that way as well. So this is going to be E little x, E little y, and then EZ. Okay, so I'm going to look at that section here, and I'm going to take this creature so that it doesn't clutter our situation. So I'm just going to do that here. I'm going to scoot that and bring it here, and then look at that small section now. Okay, look at the small oval or circular section at G, and then construct the sequence using that. Construct the 3-1-3 sequence using that segment. Okay, segment or section. Alright, so I'm going to take that and copy that creature. Alright, and then I'm going to start off with the first of the rotations. Okay, so the first rotation in the sequence of the 3-1-3 sequence. Okay, and in this case I have my situation from before. So this is the situation that I have. I had a coordinate frame that was set up as the following. So this is going to be EZ, then I'm going to call this as E little x. Okay, and then I'm going to call this as E little y. Okay, so EX, EY, and EZ is a body fixed frame, so I just want to make a note of that as well. Okay, the frame EX, EY, EZ is a body fixed frame, but not co-rotational. Okay, which means that this little EX, EY, EZ does not rotate with the spinning top. Okay, so just to point out what that is, that is that guy, and then this is that guy. EX, EY, capital EZ is the inertial frame that has been set up. Okay, All right, so this is the situation I have. Now I'm going to take the first rotation and perform it about the EZ direction. So I have to create some space for myself. So I'm going to scoot this down and bring it here. Okay, the first rotation is about the EZ direction. So that is going to be drawn in the following manner. I'm going to rotate it by an angle phi. Okay, so that my new rotated coordinate frame is going to be looking in the following manner. So I'm going to call this as E1 prime, this is E2 prime, and then I'm going to have E3 prime here, which means that this is the same as EZ, and my rotation is going to be about this by an amount, as you know from before. This is going to be phi dot, which means that this angle here is going to be an angle phi, and that angle there is also an angle phi. Okay, so the first rotation is performed with respect to the EZ direction, and you have the E1 prime and the E2 prime axes, which is now the new position. Let's say they were initially coincident with this EX, EY, EZ coordinate frame, but then this is their new position. Okay, so in this case here is what we're going to be saying. Okay, so the first rotation performed by rotating a body fixed frame by an amount phi dot about the EZ direction. Okay, and this is the same as what you've seen in the past. Okay, we did this for the rolling coin, so there is nothing much of a surprise here. And if you do the coordinate transformations, then you can quite clearly see that E1 prime is going to be cosine phi EX plus sine phi EY. E2 prime is going to be minus sine phi EX cosine phi EY, and then E3 prime is going to be the same as EZ. Okay, and if I call this as frame F1, and if I call this as I'm sorry, I have to call the other one. Okay, this one is going to be called as frame F2. Okay, so F1 is E little x, E little y, E little z, or EZ, and F2 excuse me, is E1 prime, E2 prime, E3 prime, and we had F naught, let's say, is EX, EY is the inertial frame. So F naught is E capital X, E capital Y, E capital Z. This was the inertial frame. Okay, we know that omega of F1 slash F naught is 0, right? Because this is not a co-rotation rotational frame. EX, EY is little x, EY, EZ. But then we also know that omega of F2 slash F1 is going to be phi dot in the EZ direction. Okay, so that's something that we make a note of. So which means that in the first rotation, we see that omega of F2 slash F naught is actually going to be phi dot EZ. Okay, because we know that F1 related to F naught is 0, so there is not much to see here. Okay, so I'll just put a box around that so that we will grab this guy as we go back down later. And we can make these same things that we have done for the rolling coin. We can write a coordinate transformation or a rotation matrix as the following. Okay, so similar to the rolling coin, we can write a coordinate transformation matrix and this is going to be E1 prime, E2 prime, E3 prime. Okay, this is equal to the following. It's going to be cosine phi sine phi 0 minus sine phi cosine phi 0 0 0 1. Okay, this is the transformation matrix that we have, and this will be multiplied by ex, ey, ez. Okay, this is similar to the rolling coin. Okay, and let me underline that. So coordinate transformation matrix, and this is typically called as R1, the rotation matrix. And so we can say the following. We can say that E prime 1 2 3 is R1 times E x y z. Okay, where we have the following association. So this is the same as that. Okay, and then this is the same as that guy, maybe a different color. This creature is the same as that is the rotation matrix. And then lastly we have this guy is the same as that guy. Okay, so these are the rotations that we have. And the story continues. We take the first rotation, which was done about the 3-axis or the z-axis, then we tilt it, rotate it about the 1 direction, which is a new 1' axis. And then once we do that, we go ahead and we write the rotation sequences, and the same way as we did for the rolling coin, and move forward. Okay, so let's go to the second rotation of the rotation 313 sequence. Okay, so this was the first rotation of the 313 sequence. So the second rotation of the 313 sequence. Okay, this will be performed about the 1' axis. Okay, will be performed about the 1' axis. This is similar to what we saw for a rolling coin. Okay, and I want to hazard drawing this now. Let me try doing that. Okay, so here is the situation from before. So perhaps I should draw the figures first and then bring out all these guys. Okay, so let me first do it. So I had a situation where this was the top or the location of that segment, if you remember. Okay, then I'm going to duplicate this, and then I'm going to take this guy and tilt it. Of course, I have to perform the tilt. I'll first perform the tilt and then I'll bring it here. Okay, and I want to style this by saying, okay, this is going to be green in color. The filling is also going to be green. Yes, the stroke is going to be red. Okay, all right. So this is the situation that we have, and I'll draw the axes first of all. We had the z-axis, which was passing through here. Okay, then previously we had the x-axis and the y-axis as drawn. Okay, these were the axes. Then we said that, okay, hey, I'm going to take these axes and I'm going to rotate them, okay, such that here is the situation I have. Okay, that's going to be the 1' direction. Then here was the 2' axis. The 3' was the same as before. Okay, I'm going to take this and extend this a little more. And then lastly, I'm going to say that, okay, I'm going to take this axis, the one drawn in blue, and then tilt it by the nutation angle theta, so that I get the following situation. Okay, there's one there, and then there's going to be one there. All right, now let's start labeling all these creatures. Okay, so here this is going to be let me do the labeling in the black color. Okay, so this guy was originally E1', but the rotation is performed about that, so this is going to be the same as E1 double prime. This creature was originally EX, this creature was EY, this was E1 prime, and so this guy was E2 prime, this was EZ, okay, which is the same as E3 prime, okay. Then I have two new things. I have E2 double prime here and E3 double prime here, okay. And so if I look at the way the rotations have been drawn, the first rotation was done on this plane, okay, that was done on that plane by an amount phi. The second rotation is done by going from here to there, okay, and going from here to there, okay. This is going to be done by an amount theta, okay. And so if I take this figure, I'm going to bring this figure down here so that we have a better view of things. Sorry if it looks a little cluttered, but this is the situation that we have, okay. And I'm going to take this creature and pull it out a little more so that I'm capable of writing all these things. Alright, maybe I gotta move all of these guys and cut that off. That's not a good idea, but maybe I can copy that from here. Alright, so this was the situation I had, okay, in the previous page there, okay. Then we see that, in the initial situation, so this axis was of course the E1 double prime axis, so this was E1, which is the same as E1 double prime, and also the rotation is performed about this direction, and that is by an amount which I'm going to call as theta dot, okay. The first rotation was performed about the EZ direction, so if I extended that here, the first rotation would have been performed about that direction by an amount phi dot, okay. This is the second rotation that is being performed, and you can clearly see what the situation is, right. And so in this second rotational sequence, if I bring it onto the side here, okay, we can see, so here the top is now rotated about the E1 prime axis by an amount theta dot, okay, which implies that E1 double prime is going to be the same as E1 prime, but then E2 double prime is going to be cos theta E1 prime, I'm sorry, E2 prime cos theta E2 prime, and then sin theta E3 prime, and then E3 double prime, as you can see, is going to be minus sin theta E2 prime cos theta E3 prime, okay. This is similar to what we had for the rolling coin, okay, which means that if I now write the transformation matrix, then I have the following. So I have E1 double prime, E2 double prime, E3 double prime written as a column vector. This is going to be given by the following matrix, okay. So that's going to be 1 0 0 0 cos theta sin theta, 0 minus sin theta cos theta, almost there, okay. And this will be multiplied by E1 prime, E2 prime, E3 prime, or we can say this is similar to what we had done previously. So this is going to be E double prime 1 2 3. This is going to be R2 times E prime 1 2 3, which is going to be R2 times R1 times E XYZ, okay. And the associations as before, so this creature is the same as that. Then I have this rotation matrix is the same as that, and then lastly I have this guy is the same as that. I'm sorry, Okay, that's the same as that, but then R1 is something that we had written previously back. So this is the rotation matrix, and for reference we had R1 written here, cos phi, sin phi, and so on and so forth. Okay, which means that if I now call the double prime coordinate frame as the frame, let's say this is frame F3, right? This was frame F2, this was frame F1, this was frame F2. Okay, then we have the following. We see that omega from before, frame F2 related to F1 was phi dot Ez, and omega of frame 1 related to frame F0, the inertial frame, was the 0 vector. And we see that omega of F3 slash F2 is going to be theta dot E1 prime or theta dot E1 double prime. Okay, which implies that omega of F3 relative to F0 is going to be phi dot Ez theta dot, this is Ez, not E dot Z. This is I guess I should be getting rid of this creature here. This is Ez theta dot, and this is going to be E1 double prime. Okay, almost there. We have to perform the third sequence of rotations, and then we are on our way home. Okay, then we perform the third rotation in the 3-1-3 sequence. This will be similar what we did for a rolling coin. Okay, and to perform the third rotation, here is what I'm going to do. Okay, with your permission, I'm going to bring these creatures. Okay, I'm going to actually take just that, and then I'm going to copy that and bring that here. Okay, then we previously had the following axes, right? That was the z-axis, and then that was one axis that we had, and then here was the y-axis, right? Then we had the next set of axes which I had drawn as that. Okay, that was on the xy plane, and then Ez and E3 were the same, and then we said that okay, I'm going to take these creatures and then I'm going to tilt them such that this is now I want to draw it a little better. So perhaps I should take this guy and then do that and do that. Now I come to the third one, which is going to be this guy. Okay, I don't want to do that yet, and then I'm going to have that one. Okay, so that's the story so far, and if I start labeling them, so that's going to be EX, that is E1, which is the same as E1 E1 prime, which is the same as E1 double prime. This was EY, this was E2 prime, E2 double prime, this was EZ, which was the same as E3 prime, and that was E3 double prime. And now my rotation is going to be the following. Okay, so I need I think the red color here, and now I'm going to take it and rotate it about the E3 double prime direction. So I'm going to do the rotation about this axis here by an amount psi dot. Okay, and if I do that, I will see that the E1 double prime is now going to be tilted out. So I'm going to take these guys and bring them here. Okay, I'm going to see that this is going to be tilted out this way. Okay, and this is going to be tilted out this way, but the rotations are in the E1 double prime, E2 double prime plane. Okay, so if I draw them out, then that's going to be by an amount psi and amount psi. Okay, that's the amount psi. Okay, and previously we had this amount, which was phi. I guess I shouldn't be messing up this figure, but I just wanted to point that out. And that was also phi. Then we had this was going up, okay, and then in the same plane, okay. So I guess I don't want to show those just so that it doesn't become confusing. My lecture notes, which I'll post on Carmen, will have better figures than this. And so here is the situation. So we perform a rotation about the E3 double prime axis at a rate psi dot, so that we are going to get E1, E2 and E3. Okay, so this is going to be our new coordinate frame, so which means that we get E1, E2, E3 after the rotation. Okay, and a note that I want to make here is the following. Okay, so the first note, the first rotation was by an amount phi in the EX, EY plane. Okay, then the second rotation in the EX, EY plane and about the EZ direction at a rate phi dot. The second rotation was by an amount of theta. In which plane was this going to be? So this was going to be in the E2 prime E3 prime plane. Okay, in the E2 prime E3 prime plane, E2 prime E3 prime plane about E1 prime at a rate of theta dot. This is the nutation angle. And then the third rotation, as we see, was by an amount psi in the E1 double prime, E2 double prime plane about E3 double prime at a rate of psi dot. Okay, so these are the three rotations that we have been performing. And if I go back and take a look at my figure that I have drawn, quite cluttered, of course, I agree with you on that. Maybe I can copy that and then I can bring that creature down here. Maybe I can expand this figure so that we see each of these things quite clearly. Okay, so this is the situation. We start off with EX, EY and EZ, then we get E1 prime and then E2 prime and then E3 prime, and then we get E1 double prime, E2 double prime, E3 double prime, and then we get E1, E2 and E3, okay, by rotating it by an amount psi. Okay, and once we have this, we can write the rotation matrix as follows. So I have, okay, first of all, I can say that E1, yes, is now going to be with respect to E1 double prime. So this is going to be cosine psi E1 double prime, sine psi E2 double prime. E2 is going to be minus sine psi E1 double prime, cosine psi E2 double prime. E3 is going to be the same as E3 double prime. Okay, that is the situation that we have. All right, and we can say that, okay, if I call this as frame, I think I had this will be frame F5 because I had F0, then this was frame F1, this was frame F2, and this was frame, I guess, F3, this was frame F4, apologies. This was frame F4, and then I can immediately see that omega of F4 slash F3 is going to be psi dot E3 or psi dot E3 double prime, and then omega of F3 slash F naught from before was phi dot Ez and theta dot E1 double prime or E1 prime, which means that omega of the top, which is going to be omega of F4 slash F naught, is going to be phi dot Ez theta dot E1 double prime psi dot E3. And you can clearly see that Ez is not perpendicular to the plane containing E1 double prime and E3. Okay, this is F4. Okay, the Euler basis as we had before. Similar to the rolling coin is Ez E1 double prime E3, which is the same as E3 double prime. We can see that this is not an orthonormal basis. Okay, that's something that is quite obvious. Alright, and then we can also construct the rotation matrix as before. So from before we can say that okay, if I write this out, I have E1 E2 E3. Okay, this is going to be cos psi sin psi 0 minus sin psi cos psi 0 0 0 1. The rotation was about the E1 double prime, E2 double prime, E3 double prime, and then we can again write this in the following manner. So we can call this as E1 2 3. This is going to be R3 E1 2 3 double prime, which is going to be R3 times R2 times R1 times E XYZ. Okay, and the associations that we had as before, these two are the same. Then these two are the same, and then lastly I had these two creatures being the same. Okay, and so the entire rotation tensor for the Euler rotation is going to be R3 times R2 times R1. Okay, so the rotation tensor for the 3-1-3 Euler sequence is R, which is R3 R2 times R1. Okay, all right, and so this is a third order tensor. As you can see, there are 3 rotations that are necessary, so this is a third order tensor, okay, or rank 3 tensor. Okay, all right, so we now have most of the steps done. We have the angular velocity. That is the next step that we're going to do, right, for the coin, or not for the coin, I'm sorry, we're doing the top here. Okay, but I want to draw one more figure. Okay, this is with your permission, I'm going to copy, I guess in a sense, the smaller of these figures. So if I do that, let me take this creature here, okay, and then copy that and bring that here. So eventually we have the following situation. So this is the case. Okay, let me now draw some straight lines and complete the figure. I guess I should be making sure that this indeed does look like a top. Okay, I'll try my best. You know, somehow it sometimes lets me you know, do things nicely, sometimes it doesn't. Then I have that guy there. Okay, I'm going to take this entire setup and then maybe tilt it, reduce the size of that, and then maybe tilt it a little more. Okay, so that I get the situation here. Okay, now I'm going to set up the axis. So this was the point O, right, and at this particular point, if I scoot this over and bring it here, now I had one of the axes, the z axis, was drawn here. So this was E capital Z, right? Then I had the capital X and then the capital Y directions, which were drawn here. So this was E capital X and then E capital Y, right? This was point O, and then here somewhere was the center of mass of the top. Okay, let's assume that that is the situation there, and I'm just going to draw a straight line from here to there. Okay, I'm going to call this distance as some distance L. Okay, then I'm going to have a pair of axes that are going to come from there. Okay, so that's one. Maybe I should change the color of this. Let's see, this is better. Then I'm going to have two more, right? This is the primed the E1, E2, E3 axes that you might remember. Okay, once again I think I should have changed the color of these creatures. Okay, so let me do that. Okay, then I have the other two directions, which I'm going to draw in a minute. Okay, as you can see from here, just going to extend that guy. Okay, and I'm going to take this guy and bring that here. All right, and so if I mark the axes, this is going to be E1, E2, this is going to be E3. This is the center of mass, of course, as you know, the center of mass G for the spinning top. Okay, this is the length L, and it is also obviously seen that this entire angle here is going to be the angle theta. Okay, which means that if I take a straight line and I draw it straight out here, okay, this angle inside is going to be theta as well. Okay, and since I'm doing that, let me change the style of that line to a different color. Okay, so that we know what we're talking about. And this is the angle that I'm talking about. So all the way down to there, that is the angle theta, which means that this height that I'm talking about here, which will be useful for the definition of what our potential energy is going to be. Okay, so that height is going to be L times cosine theta. Okay, as you can see, that's L times cosine theta, and probably by that this should also be in the color black. Okay, and here is the triangle that I'm talking about. Okay, so that's the triangle, and that's the height L cos theta. This is going to be useful for defining the potential energy. So this is the height from datum plane, as you can very well see. All right, so this is the situation that we have. Maybe now it is time for me to scoot this and bring this up a little more, so that this is the situation that we have. And based on this, we are now in a position to start writing the angular velocity in a certain coordinate frame, and then we will start writing the velocity of the center of mass, and then we should be on our way pretty much, writing the Lagrangian, and then going further writing the equations of motion, and then calling it a day. Okay, so let's do that. Okay, so in this situation, I'm going to do the following. Okay, now angular velocity of the top, omega of the top is phi dot Ez theta dot E1 double prime, and then psi dot E3. Okay, I want to express this as you can see, the distance L is in the E3 direction, so I want to express or the position vector from point O to point G is in the E3 direction, so I want to express this in the E1, E2, E3 coordinate frame. Okay, so I can also write the following. As you can see, the position vector RGO, which is essentially RG, is going to be L in the E3 direction, which means that let us express omega of the top in the E1, E2, E3 frame. Okay, this is the absolute angular velocity of the top. There's no doubt about that. Okay, and the reason for that is the following. You see, if I write Vg, this is going to be r dot g, which is going to be d by dt of L times E3, which is going to be L dot E3, L E dot 3. Obviously, you know that the length is a fixed quantity, right? Which means that this is L E3 dot, excuse me, which implies that Vg is going to be L times omega of the top crossed with E3, and hence we can see that to simplify our situation, to express omega top in terms of E1, E2, E3. This is the reason, okay? And I'm going to skip some steps here. I will be posting this on my lecture notes. My plan is to, give you a break. I know you've been plowing through my lectures, whether you like it or not. I hope you like it. But I want to give you a break and do these things a little quickly. So omega of the top, the extended thing is going to be posted on my lecture notes, okay? Extended substitution. Lecture notes on Carmen, which I will post, okay? And so this can be expressed in the following manner. So omega of the top, perform substitute for Ez in terms of E1, E2, E3. That's one substitution. Then the other substitution is I also have to substitute for E1 double prime in terms of E1, E2 and E3. Substitute for E1 double prime in terms of E1, E2, E3. Okay, and then we get the following. Omega of the top, which I'm going to say is the following column vector. This is going to be omega 1, omega 2, omega 3 is going to be written in the following manner, okay? This is phi dot sine theta sine psi plus theta dot cos phi. Okay, let me write that out properly. Sine psi plus theta dot cos psi, then phi dot sine theta cos psi minus theta dot sine psi, and then lastly psi dot plus phi dot cos theta. Okay, and this is the same as writing the following. Omega top is the same as omega 1 E1, omega 2 E2, omega 3 E3. These are the same, okay? All right, so we have omega of the top. Now all I have to do is go ahead and write Vg, which is the velocity of the center of mass of the top, okay? So now we see that Vg, which is L times omega of the top crossed with E3, okay? I'm going to skip some steps. Substitute for omega top in the E1, E2, E3 frame and perform the cross product. Okay, here is what we end up getting. Vg is going to be L omega 2 E1 minus L omega 1 E2 plus 0 E3. Okay, that's what we end up getting after the cross product has been performed, where omega 1 is the following. It's phi dot sine theta sine psi plus theta dot cos psi. Omega 2 is phi dot sine theta cos psi minus theta dot sine psi, and omega 3, which we don't have in the Vg expression, but we do have it for the overall expression for omega. That's going to be psi dot plus phi dot cos theta. Okay, so that's the situation that we have. Now here is something that is very nice. What will happen is that first of all, because we have a spinning top which a fixed point O, we see that the center of mass does not have any translation. Okay, it's not going to be having any forces that induce translation of the center of mass, unlike that of a rolling coin. Okay, so unlike a rolling coin, there will be no forces on a spinning top. I guess there will be no forces that will affect translation of the center of mass. Of the center of mass of the spinning top. Okay, which implies that since Vg, which is x dot ex, y dot ey, z dot ez, can be obtained if we know theta, phi and psi, which implies that for the spinning top there will be only 3 degrees of freedom. We end up with 3 degrees of freedom for the spinning top, which are theta, phi and psi. This is purely because the center of mass of the top does not have any effect from any of the forces. For the rolling coin, if you look at the center of mass, the translation of the center of mass is affected by the presence of the static friction forces. Okay, but that is not the situation for this kind of a spinning top with a fixed point. Okay, that is, I just want to make a note of this. So for the rolling coin, rolling coin, the acceleration of the center of mass was affected by the static friction force. During rolling without slip. Okay, but for the spinning top that is not the case. The acceleration is not affected by any of these forces at the contact point. Okay, so the acceleration of the center of mass is not affected by any of the forces at the contact point O, which is why we can see that this is a holonomic system, which means that a spinning top is a holonomic system. With 3 degrees of freedom. right, with 3 degrees of freedom, and we can now obtain the equation of motion of the top in terms of generalized coordinates, which we will select as phi, theta, and psi. This is the thing for the spinning top versus the rolling coin. The rolling coin was a non-holonomic system, but the spinning top, because of the fact that the acceleration of the center of mass is not affected by any of the forces at the contact point, we can say that, okay, hey, my constraint that the velocity of point O was fixed gives me 3 constraint equations, and I started off with configuration coordinates which were 6 in number. I have 3 constraint equations, so I end up with 3 degrees of freedom, and I can choose generalized coordinates, okay, for the spinning top. Okay, so these are going to be my generalized coordinates. So we can obtain the equation of motion of the top in terms of generalized coordinate. This makes it a really simple problem. Okay, all I have to do is write the Lagrangian and then differentiate and go on my merry way. Okay, so here is what we do next. Okay, so far we have kinetic energy is going to be T translation, okay, plus T rotation, okay, and so this tells me that T is going to be half m Vg square half omega I center of mass omega, and I can choose any bases for writing the rotational kinetic energy. We have done this some time back, which we call as a change of bases. We had spent quite a good amount of time talking about rotation matrices and so on at the during the middle of the semester, right before we went into the Lagrangian formulation. Okay, so that's something that you can go back and take a look at. So it's fairly straightforward to write now. We know that okay, this is going to be half times. So I know from before. I'm just going to write Vg. Okay, Vg was L omega 2 E1 minus L omega 1 E2. Okay, and then I had omega was omega 1, omega 2, omega 3 I center of mass, which, because of the fact that this is a symmetric body, I can write as the following. Okay, I can say that this is I1, I2, I3, which I'm going to say is I prime 0 0 0 I prime 0 0 I3. Okay, where we say that I prime. Okay, just say that this is the situation. Okay, so now if I do all the substitutions, I end up getting the kinetic energy as the following. Okay, so substitute for Vg square. As you can see, this is L square omega 2 square plus L square omega 1 square and omega and ICM into expression for kinetic energy T, so that we get kinetic energy T as half times, after simplification. Okay, I'm getting this to be half times omega 1 square plus omega 2 square times I, and hang on and I'll tell you what that means. Okay, and this is going to be half I3 omega 3 square, okay, where I is I prime plus ml squared. Okay, I'm skipping some steps here just so that we complete this problem fairly quickly. Then if I start substituting for omega and 1, 2 and 3, okay, then substitute for omega 1, omega 2, omega 3, okay, into kinetic energy, and then simplify. I get kinetic energy T to be the following. Okay, this is going to be half times I times theta dot square phi dot square sine square theta plus half I3 times psi dot plus phi dot cos theta whole square. Okay, then potential energy. V is mgh. What is this height h? If I go back and bring my figure from before, okay, if I take this creature and I bring it down, okay, you can immediately see what the height is going to be. Shrink this in size. You can immediately see that V is going to be mgl cos theta, and this was the kinetic energy. This was V, which means that the Lagrangian L can be written as L is T minus V. So L for the spinning top is going to be half I theta dot square phi dot square sine square theta half I3 psi dot phi dot cos theta square minus mg L cos theta. Okay, and so if I write this a little more cleanly, okay, so we have L is half I theta dot square phi dot square sine square theta half I3 psi dot plus phi dot cos theta minus mgl cos theta. Okay, so this is the Lagrangian, almost there at the end of the problem. Okay, all right, and then there are some interesting things that we can see. First of all, there is so the weak torque that I mentioned is due to the potential energy term mgl cos theta. You can see this is a weak torque, so perhaps that is something that I should circle out here. We can see that this particular term here is the weak torque due to gravity, which is why the reason why we call it a heavy top. Okay, so this is the reason we do it that way. Okay, one thing that is quite interesting to see is the following. Okay, if I look at the Lagrangian, okay, before that, this is a conservative system. Okay, so the since there are no applied external forces and no dissipative terms, this is a conservative system. Okay, which means that if I write the Lagrangian formulation, I'm going to have d by dt dl by d phi dot is dl by d phi plus q phi nc. Okay, likewise I'm going to have d by dt dl by d theta dot is equal to dl by d theta q theta and c, and then the third thing is d by dt of dl by d psi dot is equal to dl by d psi, and then q psi nc. And obviously you can see that since it's a conservative system, all these terms are gone. Okay, all these terms are gone. And what we can also say is the following: in this case we don't use Lagrange multipliers, okay, because we see that it's a holonomic system based upon what we have seen earlier. Okay, so we don't use the Lagrange multipliers here, so I just want to make a note of that. So note that in rolling coin we used Lagrange multipliers since our system was non-holonomic, okay, which means that for the rolling coin the Lagrangian formulation had to be written using the configuration coordinates. Plus the Lagrange multipliers. Okay, so this is a key statement for the rolling coin. The formulation had to be written using the configuration coordinates and the Lagrange multipliers, but for the spinning top, okay, we don't have any such issues. The Lagrangian formulation can be written in terms of the generalized coordinates, and we don't need to use the multipliers. Okay. Lagrangian formulation can be written in terms of the generalized coordinates, and we do not need to use the multipliers. To obtain the equation of motion for a spinning top. Okay, so for the spinning top, the Lagrangian formulation is written in terms of the generalized coordinates, and we do not need the multipliers. Okay, this is a fundamental difference between the two formulations. So with that being said, let me bring in some of these terms here. Okay, so I'm going to take all of these guys, I'm going to copy that. Okay, and then so for the spinning top, okay, we have first of all this guy. These are actually the equations of motion in phi, theta and psi coordinates. Okay, one more thing, the Lagrangian is from before here. Okay, so I'm going to bring that creature as well and clean up some of these things. Okay, so I'm going to copy that and bring that here. Okay, and I'm going to cut off some of these. I guess I have to completely get rid of that term. Let me rewrite it. Okay, minus mgl cos theta. Okay, and so here is something that you see, something very nice in the spinning top. You see that if I look at the Lagrangian, it is independent of the angle phi and the angle psi. Okay, the Lagrangian is independent of phi and psi which implies that dl by d phi is equal to 0, dl by d psi is equal to 0. And I'm not going to go through the details of this. This is something that I'll be posting in my lecture notes, which you can take a look at. Okay, in this situation, phi and psi are called ignorable or cyclic coordinates. Okay, ignorable coordinates or cyclic coordinates typically tell us something about conservation of momentum. Okay, so these typically tell us about tells us about momentum conservation, momentum symmetry, or conservation, about certain directions. And if you remember, this was one of the last things that I had discussed when we actually quit before spring break. During just before spring break, we had looked at a problem using the Lagrangian formulation, and I had spoken to you about something called as ignorable or cyclic coordinates, and I showed you that there was a conservation of linear momentum taking place in these problems. For the spinning top, you'll see conservation of angular momentum. Okay, I'm not going to go through the details of these. I will be posting these on my lecture notes. So once you do the substitutions into the Lagrangian formulation, here is what we end up getting. Okay, so after substituting, for L in the Lagrangian formulation, for the spinning top, okay, we obtain the following equations of motion. Okay, in the phi direction, for the phi generalized coordinate, this is the equation that we end up getting. It's going to be d by dt of I sine square theta phi dot plus I3 cos theta times psi dot plus phi dot cos theta is equal to 0. Then in the theta, after I do the substitutions, I end up getting I theta double dot is equal to I sine theta cos theta phi dot square minus I3 times psi dot plus phi dot cos theta sine theta phi dot mg L sine theta. As you can see, that's a part of the theta equation of motion, and then the psi equation is d by dt of I3 times psi dot plus phi dot cos theta is equal to 0. Okay, these are the three equations of motion. In my lecture notes, I will be posting about precession motions. Okay, lecture notes on Karman, precession of a top, and nutation motion of a top. I will be posting this on Karman. Okay, and one very last thing that I want to make a note of, when I looked at the rotational sequences, I'm just shy of 1.5 hours, so I just want to make a note of it. If I go to the second rotation, right, or if I look at this particular figure here, if I look at this particular figure here, let's say, okay, if I say that Well, I guess I should look at this figure. If I say that theta is equal to 0, then you see that I'm not able to distinguish between the phi and the psi rotation. So the geometric singularity for the 313 sequence is theta is equal to 0 here. Theta is equal to 0 or theta is equal to pi. Okay, so I just want to make a quick note. For theta is equal to 0, we get a geometric singularity. Okay, geometric singularity means that we will not be able to distinguish between the phi and the psi rotations. That is, we will not be able to distinguish between the phi and the psi rotation. So there is always going to be some kind of a singularity associated with any sequence of Euler angles, whether it be a 313 or a 321. Okay, but we as long as we assure ourselves that okay, theta is not going to be 0 degrees, it's going to be somewhere in between 0 and pi, then we are good to go. Okay. All right, so we come to the end here. This is the last thing that we wanted to do. Okay, one thing that I also had wanted to do as the semester had begun earlier was to talk about a brief introduction to chaos theory. I'm still going to post lecture notes on Carmen for that. I hope you'll be able to take a look at it. It's very interesting. I'm going to look at in the lecture notes. Of course, I'm not going to be doing that on here. But in the lecture notes, I look at a simple pendulum system with base excitation, or I take the pivot and then I excite it using a sinusoidal excitation, and I'm looking at it in the presence of damping. And for very small changes in certain control parameters, the long-term behavior of the system is wildly unpredictable. And that is the basis of chaos, the essence of chaos. Chaos theory. Okay, so please take a look at it. I'll be posting it on Carmen, and we come to the end of our ME 5030 lectures. It's been a great pleasure. I wish we had met in person. We would have been able to, relate many of these concepts to what we talk about in day-to-day movements of bodies a little better, I feel. Maybe I could have answered more questions better. But I hope this has been useful to you. It's been a great pleasure on my behalf. I hope you're staying safe and staying healthy. As I said, we will have a take-home exam which I'll be posting on Monday this coming week, and I'll give you 3 to 4 days for that. A few problems, essentially using Lagrange multipliers, and maybe some basic concepts from the rolling coin. Okay? All right, take care of yourselves. I'll be conversing with you over emails on Carmen. Okay? Good luck.